Okay, good morning. I'm going to try this for the third time. I've made 3 videos and all 3 have failed, so one more time. If this doesn't work, then you have the day off. Today we are going to do a post-lab um, from our marble ramp lab. And I think this is the period 3 class that actually did the lab. So you guys actually did the lab, and hopefully it makes sense to you. I'm going to use this data that I got from Casey and Ryan. Their data was perfect. Casey, particularly, I took most of your data, and Ryan, I used yours to corroborate Casey's data, and it looked good. So I'm going to use this for my other class. They were not able to do the lab, but they were able to look at the data and hopefully get the same conclusion. So remember what we did. We had a ramp set up here, and we were releasing marble from various locations on this ramp. And we were looking at how the point of release affected the velocity of the marble as it came off the table, and then where the ball landed on the ground as a result of that. And I think most of these conclusions are pretty obvious. If I release the marble from higher on the ramp, I would expect it to be moving faster at the bottom of the ramp, and therefore probably travel farther out on the floor. And for the most part, I can't imagine anybody not getting that data. But the thing I want to look at is the time it took for fall to the ground. That's the thing that's a little subtle. So we're going to go through this in a little bit of detail and make sure it makes sense to you. I think 3 of the 4 conclusions make sense. It's just one of them's a little, for a lot of kids, it's a little sketchy about why that's the case. So let me go ahead here, and unfortunately my camera's in the way, and I forget how to move this thing around. So we'll get that in a second. But anyway, so if you look at the data table, I changed the data table from period 3 class to incorporate the recording of the time that the marble got to various locations, and then we took the difference. You guys just got the delta. So remember what we did. We took the marble and put it 20 centimeters up on the ramp. We let it go. The marble rolled down. Then the marble rolled across a horizontal portion. Now, when the marble's on the ramp, it's accelerating. Gravity's pulling the marble down faster and faster. But when the marble gets on the horizontal section, and we know this distance to be 30 centimeters, when it gets down here, it's not accelerating. Gravity's not affecting it. And therefore, we have, if we use equation 2, we can calculate the velocity of this marble if we know the distance and know the time. So the 1/2 AT squared goes out, so D equals VIT. Now, if I know the D and I know the T, I can calculate the V, and that's what we did. We said, hey, I know this is 30 centimeters. I know the time it took to travel using the app. Gives you a pretty good time. And we calculated the velocity. So we said 30 centimeters divided by this time yields that speed. So if we release the marble from up here, it came down, it moved across the table at a certain speed, and it turns out to be 0.41 meters or 41 centimeters per second. So that took a little less than a second to go 30 centimeters. So it's going about 41 centimeters per second. If I release the marble higher onto the ramp, I would expect it to be going faster down here, and that's exactly what happened. So if I released it twice as far up, it took less time to travel that 30 centimeters, and therefore it was going faster. It was going 88 centimeters per second. And if I released it higher and higher and higher, I have over a meter per second, 128 centimeters, 144 centimeters. So this data is perfect. If I release it higher on the ramp, it should be going faster across the table. And if it's not slowing down, then it should be coming off the table at a pretty good speed as it's released higher. So what we wanted to look at next was how far it traveled as a function of how fast it is moving. So that's this last column, range, the distance in the x direction. Well, if it's moving slowly in the x direction, it went 27 centimeters. If it's moving faster, it goes farther. If it moves faster, it goes farther, faster, farther. So as you put the marble farther and farther up the incline, it was coming off the table faster and therefore went farther out away from the table on the range. And again, I don't think that's surprising. So these 3 columns, 1, 2, and 4, make total sense. It's column 3 that gives people some trouble. And that's looking at the time it takes for the marble to fall. So if the marble was simply dropped from the ground, and this is where I combined some data from Casey and Ryan, I think, and some other people. I combined the data and came up with an average of about 0.398 seconds. For if I just dropped the marble off the edge of the table, drop it from here, it took about just under 0.4 of a second. But if I look at the marble being shot at various speeds, because remember, at higher locations, it's going faster, and therefore it's traveling faster and faster in the horizontal direction. How does that affect the time? Well, if we look at these numbers, from the first trial, it actually went down a little bit, then went up a little bit, then went up a little bit more, then went down, then went up. If you look at these 5 numbers, 6 numbers, they're almost identical. And that's kind of counterintuitive for a lot of people. A lot of people think that, hey, the marble that's dropped straight down only has to travel straight down, whereas the marble shot has to go out to the right as well. And for some reason, people think that this is going to take more time to fall. It's a very common, and I kind of get it, but it turns out that's not true. Our data clearly shows that even though there's a variation, these numbers are almost identical. If you look at this trial right here, 0.401 and 0.405, they're off by 4 1,000ths of a second. And when I say off, I don't mean wrong, I just mean different by. So even though we're moving much faster here, this thing was barely moving, here it's going much, much faster and traveling much farther, their times to hit the ground are almost identical. In fact, all these times are almost identical. So that's what this thing in red says. It says, does the horizontal speed and therefore the path of the marble coming off the table have any effect on the time it takes to hit the ground? And the answer is no. The time is independent of the motion in the x. And that's the big conclusion I want you to see. And in fact, we could actually calculate this. If we were to calculate the time it took to fall, let's just think about the falling straight down. If I put the marble here and just dropped it, the VI is 0, the A is 9.8, the distance, this varies a little bit based on which table you're at and where you held it. But if I hold it right at the edge of the tabletop and drop it, it's going to fall that distance with that acceleration with the VI. If I use equation 2, and calculate using the D equation, I come up with a time of 0.39 seconds. I think it's actually 0.388. Now, if I go back to Casey's data, let me get this thing out of the way. Look at your data, 0.388. 0.388 is exactly right. This is off by a fraction. So these numbers really support that the time is independent of the motion of the ball. The time it takes to fall doesn't care if it's moving to the right or not. And that's the big conclusion. So in your notebook, this is the part I'd like you to write down, is that the motion of an object in the x direction, so the fact that it's moving in the x direction, is totally independent of the motion in the y. The two motions don't care about each other. The vertical motion is controlled by gravity, and the horizontal one is controlled by the inertia of the ball. We'll talk about these laws later, but they're just independent. The motion in the x and the motion in the y are totally independent from each other. Now, we saw this with the boat on the river, so this shouldn't be all that surprising. And again, the boat in the river thing is kind of counterintuitive. If the boat is moving at a certain speed across the river, it doesn't matter how fast the current's flowing. So if I have the boat moving at 12 meters per second across the river, it takes some time to get across. If you're going across a lake and there's no current, it takes a certain amount of time to travel a certain distance. If the river is flowing at a different speed, it doesn't affect the time it takes to flow. And it's kind of the same idea. Although the path overall is longer, the velocity in the north-south direction is fixed and the distance is fixed, it's going to take the same amount of time. Now, another way of saying that is the horizontal motion does not affect the falling time. Both objects fall at the exact same rate. Now, I can't do this demo, obviously, but I'm going to show you what Mythbusters did. If I take a gun and I take a bullet and put it in the gun and I fire that bullet perfectly horizontally, obviously if I fire the bullet up or down, it's going to be different. But if I fire the bullet perfectly horizontally, and I take an identical bullet and hold it the exact same height. Now remember, the mass doesn't matter anyway. I could take a bowling ball. But if I take an identical bullet and drop it from the exact same height, and I shoot it from the exact same height, which one will hit the ground first? And a lot of kids will think that the shot bullet takes longer, because look at the path. It's got to go much further. But it really doesn't, because this has an initial velocity of 0. Gravity is making it fall a certain distance. This is being pulled by gravity the exact same for the vertical distance. And the fact that it has a horizontal velocity, well, all this velocity is in the horizontal direction. None of that velocity is pointing downward. So it's starting from rest also. So in theory, it should take the exact same amount of time to fall in whether it's dropped or shot. Now, Mythbusters did this.
Mythbusters are testing our real doozy. Everything's hot, ready to go.
So Mythbusters did the exact same thing.
Bullet drop.
They shot and dropped the bullet. Now, what they're trying to do is they're firing a bullet horizontally, and they have an electromagnet trying to drop this bullet, and they're having a hard time. So there's 2 minutes of the video. They're trying to synchronize the drop with the shot. So finally up here, about 2:30 or so, they finally get the thing shot and dropped the same.
And after a few test fires and a bit of fine-tuning, it works.
You can see the bullet being released up here.
It's good. It's good. It's 1/3 of a millisecond difference. Wow.
So very, very precise. The drop bullet's slightly behind, but very, very tiny amount.
which means rolling up the room 360 feet to stake out a drop zone.
Now, they actually went outside and shot a bunch of bullets horizontally and found out where they're going to land, and they came up with a number, and they're rolling up the distance. But you could actually calculate it. Maybe we will. You can use the kinematic equations to figure out where that bullet's going to land, and it turns out to be there's a little air resistance that affects the values, but that's what Adam's doing. He's rolling up and finding the drop zone. They're going to fire the bullet from down here, and they're going to drop the bullet at the other end. So the bullet that's dropped and the bullet that's shot hit side by side, and they'll have high-speed cameras to show you the effect.
Right about there. That's where they were landing out in the shooting range, so this is where I expect them to land here. Okay. Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history. All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet drop versus fired. In 3, 2, 1.
A couple different views. They're going to show you slow-mo in a second.
360 feet away, the boys can't see exactly where the fire.
Now, this is super high speed.
Let's go see where it hit.
I got to get a unit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
You see the paper's cut by the shot bullet.
And the results are simply ripping. Can't get much closer than that.
And there's the drop
Can't
bullet
wait to see
side
the
by
high
side.
speed.
Now they're going to show you. They're going to show you high speed, but they're going to do slow mo too.
Carved a streak right under the drop zone. I think this might be the shot we've been looking
This
for.
next one's good. They
In real time,
highlight
it's
it.
impossible to tell what happened.
Here's the
Adam
highlight.
analyzes the
Drop,
high
drop,
speed
drop, drop,
and
drop.
crunches the numbers.
Point. Now there's definitely a time differential, but the time is almost identical.
Divided by 6. Dude, the difference is 39.6 milliseconds, which means it's less than you and I can make out.
So it's essentially within the margin of error. It's essentially the exact same time. There is a component of it going through the air, and there is some resistance there. And again, it shouldn't affect it much, but I think it's more the fact they released it from different times. The synchronized dropping was not the same. Now, I've actually done this in class, not with a bullet, obviously. We have an apparatus that I'll show you. This is super slow-mo shot in the past. And if you look at this, here I'm risking my life on the table, but if I drop the marble, it's going to drop straight down. At the same time I fire it, a marble's going to be shot out this way. And you can see it, but you can also hear it. So they hit at the exact same time. Let me show you. Now I have a different version of this. This was last year, I think, or a couple years ago. But the backgrounds are pretty crappy. I apologize. I really have to get a big giant white sheet or something so you can see it a little more clearly. But it's the same idea. You drop it and shoot it. You can see the marbles flying through the air. But listen, they hit at the exact same time, or really, really close to the same time. So that just shows you what we were talking about. So we have it in lab, and we have it in video that the shot and drop are the same. Now, sometimes I still have students who go, well, I still don't believe it. And I don't know what else to do other than show you data and show you a video. But there's another way of looking at this from a frame of reference. And you remember at the start of the year, I talked about frame of reference. And people always ask, why do I need to know frame of reference? And this is really why I talk about that, to make this other point. Let's imagine we have a person standing motionless, and they're observing two spheres, two balls. The blue sphere is going to be dropped vertically downward. So from his perspective, this ball is falling straight down. And from his perspective, there's a yellow ball being shot out, just like the bullet demo, from the same height, only horizontally, and it's going to fall to the ground. And there's going to be an arced, parabolic yellow path. So somebody might say, well, I think the yellow ball, because it's traveling this arc, is going to take more time, even though we know it should do the same. But let's change our frame of reference. Rather than this person being stationary and watching this ball drop straight down and this ball travel on an arc, let's have this guy run alongside ball B. Well, what do I mean by that? We're going to drop ball A and we're going to fire ball B, the yellow ball, off to the right, but this guy's going to run next to the ball. So if you're running next to the ball, it's like you in a car driving next to a bus on the highway. The bus and the car have relative velocities of 0. They seem to be not moving. So if this guy runs next to the ball that's being shot, he's going to see the ball fall straight down. And he's going to see this ball moving away from him in a parabolic path. That's a little heavy to first grasp, but if we have this person, the observer, moving with ball B, he's going to see that one fall straight down and the other one moving in the arced path. Well, you can't have this yellow ball beating or losing to the blue ball, because you can't have one result in one frame of reference and have a different result in the other frame of reference. So the two spheres must hit the ground at the exact same time. They have no choice. Now that's a little heavy, but again, hopefully you believe what I'm telling you from our data and from the other videos. This was another really cool video done by Mythbusters. They did something similar. It's kind of a cool idea. They took a soccer ball and they built a gun. It's like an air cannon that fires the soccer ball. And they figured out the speed at which the soccer ball is coming out of the air cannon. It's about 50 miles per hour. So they got this high pressure cannon. They put the soccer ball in there. They fire the thing. Out comes the cannonball. Out comes the soccer ball at 50 miles per hour. Now, what they realize is if the ball's being shot at 50 to the right, and if they drive a car 50 to the left, the ball should be vector addition of 50 plus minus 50 should add up to 0, so the ball should fall straight down. And in the video, it's going to look like the ball's just coming out of the tube, like the tube just left it behind. It's like pulling the tablecloth out. But the ball is actually being shot to the right as the car moves to the left. And you're going to see, yay, vector addition.
I have a feeling that we are very close to a perfect demonstration. We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a
matching
perfect
the
release.
speeds. Now Grant sounds like
I don't know about you guys. That looked pretty good to me.
Grant
Let's
sounds
check the
pretty
high speed.
relaxed. Let's put it that way.
It really looked good to the naked eye, but the judge in this case is the high
Let's check out this perspective.
Oh my God, it's like a cartoon. It's just in the air. It stops and it just falls.
Look at that. Fantastic. I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it! Yeah! Vector addition! Yeah!
Yay, vector addition. It's my favorite quote of the year. Even math teachers don't get that excited about it. So I just wanted to show you that. Like I said, today's going to be a relatively casual day. Just watch that video, got down those key notes. On Monday, we're going to learn how to do, or next week sometime, we're going to learn how to do the calculations for these types of things. And then, like I said, we're going to try to get outside to show you something else. I'm purposely not telling you something because I want to have you outside to play around. If the weather doesn't work next Wednesday or so, then we may not be able to do that lab. If I can get the gym or the aux gym, we'll try it down there if the weather doesn't hold. But anyway, hopefully it makes sense. Hang on to that. The rest of the period you have free. Hopefully that was about 20 minutes worth of me rambling, and hopefully that works for you. Okay, so let's try to stop sharing. And if this thing, I've done this 3 times, it's erased this all 3 times. So if this happens again, I'm going to take the rest of the month off.